Welcome to my YouTube channel. I am Archie Francis Deban. Don't forget to subscribe and press your like button. So today we will be dealing with balancing of redox reactions using oxidation number method. Now, in the course of us balancing our redox reactions, we must be acquainted with the oxidation number, how to calculate our various oxidation numbers, because we'll actually need them in the process of doing that. So, for the sake of those who may have forgotten the oxidation number, how to balance, how to get or determine the oxidation number of an element or a compound or whatever it is. So, we will begin with the balancing, with the determination of what oxidation number first. So, in the course of doing that, when we're done with that, we'll go down to the balancing. So, let's start with the rules. First, we say the oxidation number, permit me if I have to read that, is defined as a charge which an atom appears to have. An atom appears to have. When electrons are counted according to some rather arbitrary rules, or better say, it can be represented as a way of numerical expression, the oxidation state of an element in any of its compounds. So we determine the oxidation state. For example, if I have H2SO4, which is tetraoxosulfuric acid, I will be asking you to determine the oxidation state of sulfur in that compound. Let me give you a practical example. I have H2SO4. This is tetraoxosulfuric acid. According to the rules of oxidation number, which I'm going to read them to you, we say the oxidation number of all elements or compound in their free state is equal to 0. Definitely, I can now equate this to 0. And now, I have to know what is the valence state of hydrogen, of oxygen, in the course of my determining what the oxidation number. So I will say hydrogen is 1, so it's 1 times 2, 1, then plus sulfur is what I'm looking for, plus oxygen is minus 2 times 4, is equal to 0. But now, the question is, how do you know, or how will you know that hydrogen is 1? That oxygen is minus 2 and not minus 1. That the halogens are whatever they are. Potassium is plus 1 or calcium is plus 2. How do you know that? So in our course of us knowing that, I will take us a little backward from the knowledge of, how they call it, the 20th element and the periodic table. So if you remember your 20th element and you also remember a little of your periodic table, we'll be able to fix that appropriately. So let us go a little backward before we can get down to this. Now, I want to determine the oxidation state of potassium, or the valence state. We call that plus 1. We say potassium is plus 1, but how will I know that it is plus 1? Then we go. We say potassium in its electronic configuration, or the atomic number, is 19. So we say this is potassium, atomic number is 19. We go to our electronic configuration process, the old method, which is 2, 8, 8, 8 plus 16, 17, 18. 1 will give us our 19. This is the old method of determining what the electronic configuration of potassium. Which means we can easily say potassium have, in the first share contains 2, in the second share contains 8, now in the last share, in the third share contains 8 again, and in the last share it contains 1. Now, from here we can now determine the group in which potassium belongs in the periodic table, and even the period when the case arises. So it has 1, 2, 3, 4. It has 4 shells. It is found in period 4 in the periodic table. And it has 1 electron in its outermost shell. It is found in group 1. So, for me not to be doing this whole thing, you can easily look here, 2, 8, 8, 1. 1, 2, 3, 4. 4 shells. So it says shells, 4. Group, the last one in the outermost shell is 1. Therefore, potassium belongs to group 1. Period. Period 4 don't show. It has 4 shells. Then period 4 of the periodic table. So that's potassium. So the valence state of potassium is +1. So if I want to determine my compound, let me say potassium whatever, that potassium now has oxidation state of 1. I don't need to go far. Now, if I have calcium, for example, let me take out this, I'm done with this. Calcium is 280, atomic number is 280. So this is my calcium, 280, that's 2882. Calcium is found in, it has 4 shells, which is period 4. And it has 2 electrons in its atomos shells, which means group 2. So the valence state of calcium is +2 because the number of electrons in its atomos shell is +2. And so on and so on. Magnesium 2 is 12. Let's take magnesium 12, which is 282. It is in period 3, group 2. So the valence state is +2. Aluminium. What is the atomic number of aluminium? Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, sodium, magnesium, aluminium. That's 13. So now, if we have our aluminium, which is 13, this is 283. It is found in period 3, 1, 2, 3, because there are 3 shells, and it is found in group 3 because it has 3 electrons in its atomos shell. So the valence state of aluminium is +3. Now there are certain other compounds or elements that have variable oxidation state, which means they have more than one oxidation state. Some like sulfur and so on, even carbon, many more. So those ones we don't determine them. So any of the compounds we're going to be dealing with must have a vivid word valence state, which we are going to use in the course of our experiment. So now, what about group 7? Those in group 7, the halogens, all of them have a valency of -1. All the group 6, which is oxygen, oxygen is -2. Sulfur has variable oxidation state, so many a time we look for the oxidation number of sulfur in a particular compound. So it is not unique, it's not static, it changes because sulfur has a variable oxidation state. So on and so forth. Now, oxygen, like you will see in the course, when I give you the rules, is always -2 for oxygen, -2 in a normal compound, but in a peroxide, it is -1. So any compound you deal with that is a peroxide, the valence state of oxygen therein becomes -1. But like H2SO4 is -2, magnesium oxide is -2, and so on and so forth. So let's take the rules of oxidation number so that we can proceed further. I will read them. Permit me, just pay attention. Number 1, I will say the oxidation number of an uncombined atom or any atom in a molecule of an element has an oxidation number 0. For example, it's an uncombined. So if I have H2, the oxidation number of hydrogen molecule here is 0. Sulfur uncombined is 0. Magnesium on itself uncombined is 0. On its own, it is 0. Now, we have oxygen, we have sodium, we have sulfur, phosphorus, all of them in their normal state uncombined with any other element. They are all what? 0. 2. In most compounds containing oxygen, the oxidation number of each oxygen atom is -2. But in compounds like hydrogen peroxide, which is H2O2, the oxidation number therein is -1. 3. In simple ions, these are compounds that have charges in them. In simple ions, the oxidation number is equal to the charge on the ion. So if I have aluminium 3+, the oxidation number of aluminium here is equal to +3. If I have SO4 2-, the oxidation number of this compound is -2. It's equal to the charge on the ion. And so on. We have ion 2+, ion 2+, ion 3+, and so on. The oxidation number of ion here is +2, here is +3, and so on and so forth. We're only explaining, we haven't started here in the calculations. We just have to get acquainted with whatever we're going to be dealing with, so that we'll not be too far apart from the other understanding part. 4. The algebraic sum of the dissociation numbers of all the atoms in an ion is equal to the overall charge of the ion. That is that of the one I just gave you, the SO4 2 minus. So this is SO4 is equal to minus to the overall charge. The algebraic sum, the last one, the algebraic sum of the oxidation numbers of all the atoms in a neutral compound is 0. A neutral compound means a compound that does not have charge in it. So if I have calcium triiodocarbonate 4 in its neutral state, this is equal to 0 to begin with. So if I have HNO3 in its neutral form is equal to 0. H2SO4 is equal to 0, and so on and so forth. So these are the rules. Get yourself used to them. Then with this, we can take our first question. Question number 1. Calculate the oxidation number of manganese in KMnO4. Question number 1. The oxidation number of manganese in KMnO4. We're going to, when we're done, we're going to find out what the name of this compound is. I don't want to tell us right now, but until when we're done. You see why? So if this is the we should find out of manganese in this compound. Now, remember the last rule is the oxidation number of any compound in its free state. Neutral form is equal to 0. So therefore, this becomes equal to 0. Now, what is the oxidation state of potassium? Well, like I told you, it is atomic number 19. It has 2881, which means that belongs to group 1. The valence state is 1. So here, potassium becomes plus 1. Plus manganese is what we're looking for. So let's still write it down. Plus oxygen. We see the oxidation number of oxygen in most cases is minus 2, unless if it is what? In peroxide, that could be minus 1. So this is minus 2. So I have minus 2 times 4. This is equal to 0. Now, this is 1 plus manganese. Plus times minus is minus. 2 times 4 is 8. This is equal to 0. If I make this the subject, I have manganese is equal to minus 8 crossover become plus 8. Plus 1 crossover become minus 1. So manganese is equal to 7. We always use plus in front of it. So this is 7. So the compound now becomes potassium tetraoxo manganate 7, because the oxidation state of manganese in that compound is 7. Let's take another question. Question to calculate the oxidation number of chromium in this compound. Let me take this out. Question 2. Cr2O72 minus. That is what they gave us. They say we should calculate, where is it? Calculate the oxidation number of chromium in this. Now remember we say the algebraic sum of the charge or the ion in a compound, either compound or whatever, is equal to what? The power, which is what? Minus 2. So therefore I can have this to be Cr2O7 is equal to minus 2. Now we're looking for chromium, but I have 2 attached to it, so this becomes chromium times 2 plus oxygen. Remember, is always minus 2. Minus 2 times 7. This is equal to minus 2. Chromium times 2 is 2 chromium. Plus times minus is minus. 2 times 7 is 14. Minus 2. I want to make this a subject. So I have 2 chromium is equals to minus 2. This crossover becomes plus 14. 2 chromium is equals to 12. Divide both sides by 2. I'll have chromium is equal to plus 6. So the oxidation number of chromium in this compound is what? Plus 6. Alright. Let's take 2 or 3 more. Then we'll proceed. Calculate the distillation number of sulfur in this compound. Let me take this out now. Okay, of sulfur in this. This is 3 iron SO4. Remember, iron could be iron 2, it could be iron 3, but let's see what it is. So we want to calculate the distillation number of sulfur in that compound. Let's presume it's plus 2, then we'll see what we get. The distillation number of all the elements in the compound in their free state is equal to 0. So iron here, we take it to be plus 2 plus sulfur, which we are looking for, plus oxygen is minus 2 times 4 equals to 0. 2 plus sulfur plus times minus is minus 8. 2 times 4 is 8. Is equals to 0. So this, I make sulfur the subject, is equals to minus 8 crossover become plus 8. 2 crossover become minus 2. Sulfur is equals to plus 6. So that is iron tetraoxosulfate 6. Obviously iron 2 because we have our valence state of iron to be 2. So it's iron 2 tetraoxosulfate 6. Now let's take another compound. 3. Okay, that's 3 already. Let me give you 4. I have Na2S4O6. We are calculating the dissolution number of sulfur in that compound. Now, the dissolution number of all the elements in their free state is equal to 0. Yeah. So this is 0. So sodium is plus 1, the valence state, plus 1 times 2, plus sulfur is what we're looking for. So sulfur times 4, plus oxygen is minus 2. Minus 2 times 6, or equals to 0. Now this is 2 plus 4x minus 12 equals to 0. Plus times minus is minus. So make this, I have 4s. This crossover become plus 12. This crossover become minus 2. 4s is equals to 10. Am I right? Yes. Divide both sides by 4. Cancel this. I have sulfur is equals to 2.5. Let's proceed. We'll solve like 3 more before we move on. Let's take another one. Calculate the dissolution number of sulfur in this compound. We should calculate the dissolution number of sulfur in the compound which I want to give us right now. S2O3 2 minus. Now we say all of this is equal to the charge, which is minus 2. So I have sulfur times 2 plus oxygen is minus 2 times 3, or is equal to minus 2. 2 sulfur plus times minus is minus 2 times 3 is 6. Is equals to minus 2. Now 2 sulfur is equals to minus 2 plus 6. When minus 6 crossover become plus. Yes. 2 sulfur is equals to plus 4. Minus 2 plus 6 is plus 4. Divide both sides by 2. 2. So my sulfur become plus 2. So that's the dissolution state of what sulfur in that compound. Yeah. Let's take another one. Calculate the oxidation number of nitrogen in this compound. The oxidation number or state of nitrogen in NO3 minus. Remember, whatever we have is equal to the charge. So now I have NO3 is equal to minus 1. The charge is minus 1. Nitrogen is what we're looking for, plus oxygen is minus 2 times 3 is equal to minus 1. Nitrogen plus times minus is minus 2 times 3 is 6 is equal to minus 1. N is equal to minus 1, which is here. This crossover becomes plus 6. N is equal to plus 5. Alright, that is it. Let's take. We should calculate the oxidation number of chlorine in this compound. We're calculating the oxidation number of chlorine there. So everything is equal to minus 1. So let's take it again. This is my chlorine plus minus 2 times 3, or is equal to minus 1. Chlorine plus times minus is minus 2 times 3, 6. Minus 1. So chlorine is equal to minus 1 plus 6. Chlorine is equal to plus 5. Now let's take the question that okay, before we go into that one, let's take this other one. Calculate the oxidation number of sulfur in the following compound. Sulfur in this compound. KSH. Alright, yeah. So this, everything in its free state is equal to 0. Potassium is plus 1. Plus sulfur, which we are looking for, plus hydrogen is what? Which is plus 1. So let me just put it 1. No need. All this is equal to 0. 1 plus x plus 1 is equal to 0. Make x the subject. This is equal to this crossover become minus 1. This crossover become minus 1. Sulfur is equal to minus 2. There we go. Let's take, we'll stop a lot. Let's take questions that will introduce the redox titration to redox, balancing of redox equation to us. Balancing of redox equation to us. Let's go. Now the question here says we should calculate the charges in the oxidation number of the following atoms in bold print at the beginning and at the end of the following reactions, and hence determine whether reduction or oxidation has occurred. Let me clean this. Okay, we have 2KMnO4 gone to K2O plus MnO2 plus 5O. Mn is bold, and the Mn there is also bold. They say we should calculate the changes in the oxidation number of the following atoms in bold print at the beginning and at the end of the following reactions. And we should tell if it is oxidation or reduction. So this is the KMnO4 in the reaction, which is the compositional reaction. We have our Mn here. So we want to know, does the oxidation number of manganese here increases or decreases. If it is 2 years and we have 3 years, then it increases, so oxidation takes place. If it is 5 years and it is 2 years, it reduces, reduction takes place. So let's start. We'll find the oxidation number of manganese in this compound. So I have 2KMnO4. All of this is equals to 0. Now, remember this 2 means every element inside possesses what? 2. Yeah. So I have potassium here in bracket. Potassium is 1 plus manganese plus oxygen is minus 2 times 4, all equals to 0. Now, let me expand now. 2 times 1 is 2 plus 2 Mn. Plus times minus is minus. 2 times 4, 8. 8 times 2 is 16. All of this, okay, is equals to 0. Now, 2 plus 2 Mn is equals to, this crossover become plus 16. Now, I want to take this across too. So, I have 2 Mn is equals to 16 minus 2. 2 Mn is equals to 14. Divide both sides by 2. Mn here is equals to plus 7. So the oxidation number of manganese here is plus 7. Let us see it this way. So I have my MnO2 is equals to 0. The oxidation number of all the elements in the free state is equals to 0. That is the compound. So manganese is what I'm looking for, plus oxygen is minus 2 times 2. Yes, it's equal to 0. So this is manganese, plus times minus is minus, 2 times 2 is 4. All equals to 0. So manganese is equals to this crossover becomes plus 4. So the oxidation number of manganese in this compound was 7. When we, from the reactant, the product side is plus 4. So it reduces. So there is what? Reduction. That's what the question asks. That we should explain the changes in the oxidation number of the following atoms in both ring at the beginning and at the end of the following reaction, and hence determine whether reduction or oxidation has occurred. So in this case, reduction occurred. Let's take another one of such. So, in both rings, as usual, we have F2 plus, okay, gives us F3 plus. We say the oxidation number of any element is equal to the overall charge in that what element or whatever it is. So here, the oxidation number here is plus 2, here is plus 3. So here was 2 and here is 3. What happened? It increases, so oxidation takes place. Now let's solve the last one on this before we go to balancing of redox. So we have 2 potassium ClO3. This is, we're looking for that of chlorine. Gives us 2 potassium Cl plus 3 oxygen, moles of oxygen molecule. Let's see what happens here. The 2 will go all through. I can as well just strike out the 2 because it's uniform. But then let's see. This is my 2. Potassium is plus 1 plus chlorine plus minus 2 times 3. All this is equal to 0. This side is 2, open bracket, 1 plus chlorine, close bracket, is equal to 0. This is 2 times 1, 2 plus 2Cl. Plus times minus is minus. 2 times 3, 6 times 2, 12. All equals to 0. This is 2 plus chlorine is equals to 0. Okay. Make this the subject. So 2Cl is equals to 12 crossover become plus 12. 2 crossover become minus 2. And this is Cl is equals to 2 crossover become what? Minus 2. Now this is 2Cl is equals to 10. You have also by 2. Cl is equals to plus 5. And here is this. So what happens here? The oxidation number of chlorine here is plus 5. The oxidation number of chlorine here is minus 2. It reduces. So in this case, reduction takes place. So having said that, remember our initial arrangement is to balance what? Redox equations. So like I said earlier on, we cannot balance redox equation without a fair knowledge of what? Oxidation number or oxidation state of compounds or of elements. So as such, we have to start with oxidation number. So now we have a glimpse of what it is or whatever is associated to it. So let's move on to what? Our usual what? Redox. Balancing of redox equation. In redox, it has its rules. I'll give you the rules, like I said, but I'll not write them down. The basic rules are as follows. Assign oxidation number to each atom which changes and calculate the change in oxidation number. Where 2 or more atoms change oxidation number in the formula, calculate the total change in oxidation number in the formula. 3. Balance electron transfer, that is the gain and the loss. 4. Balance oxygen atom by one H2O molecule. Balance each hydrogen atom by one hydrogen ion for acidic solution and OH negative for an alkaline solution. 6. Balance the charge by adjusting coefficients on inspection. So there will be questions that through inspection we'll be able to balance it. So let's take our first question to balance the following equation. Number 1, in balancing of redox equation. Question number 1. Mn O4 minus plus iron 2 plus gives us Mn 2 plus iron 3 plus. Okay, I think we're correct. So let's balance. This is a redox what? Equation. Now, the first thing we do is to calculate the oxidation state of each of these, either element or ions or compound, and so on. So here we go. Let's start with this. When I'm done calculating the oxidation number, I'll put the value here, then maybe clean the calculations. So I have MnO4 is equal to minus 1. As usual, remember the oxidation rule. So manganese is what we're looking for, plus oxygen is minus 2 times 4, all equals to minus 1. So we have manganese, plus times minus is minus, 2 times 4 is 8. This is equal to minus 1. So manganese is equal to minus 1, this crossover becomes plus 8. Then manganese is equal to plus 7. So here oxidation state of manganese in this compound is plus 7. Here is plus what? 2. It's equivalent to the charge. We said so earlier. Plus 2 and here is plus 3. Do we remember that rule? The oxidation rule. Let me read it again so that you know why it is so. I said earlier on, in simple ions, okay, the oxidation number is equal to the charge on the ion. So the charge on this ion is plus 2, here is plus 3, here is plus 2, so the oxidation number is equivalent to that. So now, I have the oxidation number, so I can take this out. You see the reason why you must have a fair knowledge of oxidation number in order to balance what? This redox equation. So now I am off with this. Now the next thing is, we're dealing here contains manganese, here manganese, iron here, iron here. From the product side, we have +2. From the reactive side, reactant, we have +7. So 2 minus 7 give us what? 5. Ignore the charge, so we call it 5. It's supposed to be -5, so let me just call it manganese. For the manganese sake, we have 5. -5, but it's +5, you ignore the charge. Now this side is 3 for iron, so let me call this iron. 3 minus 1, 2, sorry, is equals to 1. So this is the second step. Where you've gotten the oxidation states, the manganese to the left, the reactant side to the product side, you do your subtraction from the product minus that of the reactant, whatever you're left with is there. So the same thing goes to the iron. 3 minus this will give us 1. The next step is you cross multiply. Manganese have 5. So now wherever you see iron, you put 5 before it. Whenever you see manganese, you put 1 before it. That's just that. So now manganese is 5, iron is 1. So now manganese here, I'll have 1 in front of it. Manganese O4 minus 1 here is the same thing. Plus iron. We'll now take that of manganese, which is 5. So I have 5 iron 2 plus. This gives us manganese is 1 in now. So we have our manganese 2 plus iron is 5 iron 3 plus. Now, having done this, we balance for oxygen in the right hand side. We have 4 moles of oxygen, yes, we have to put 4 oxygen this way by introducing what? Water. For water contains oxygen. So now I can have this to be manganese O4 minus plus 5 iron 2 plus gives us manganese 2 plus 5 iron 3 plus 4 moles of water. So by this, 4, oxygen has 4, so oxygen is balanced. But in the course of we introducing our oxygen, we also introduce what? Hydrogen. So we have to balance hydrogen in the left hand side of the equation. We have 4 moles of, hydrogen, 8. So now I will add 8 hydrogen ions in the left hand side of the equation. So I have my manganese O4 minus plus 5 iron 2 plus 8 hydrogen plus. This will give us manganese 2 plus 5 iron 3 plus 4 H2O. Now, having gotten to this level, balance what? The charges. 1 times minus 1 is minus 1. Plus 5 times 2 is 10. Plus 8 times 1 is 8. 1 times 2 is plus 2. Plus 5 times 3 is 15. Now, 10 plus 8 is 18 minus 1. I have 17. Plus 15 plus 2 plus 15 is 17. So I have plus 17. Just call it 17. So now we say the equation is what? Balanced, because the left hand side is 17 and the right hand side is 17. So the redox equation is balanced. So this become our equation, which we can use in the redox reaction. In case we are dealing with titration, we have to know the number of moles of manganese and that of the oxidizing agent and the reducing agent. The oxidizing agent now becomes 1. The reducing agent is 5. The number of oxidizing agent to the number of reducing agent. So that's what it is. So we are balancing. So without the knowledge of balancing of this whole thing, in the course of doing that calculation, you're not going to get it right because you don't know the number of moles of the oxidizing agent and the number of moles of the reducing agent in the equation of reaction. So we're good with one. Let's take another one. Okay. Question number 2. You say we should balance the equation. Manganese O4 minus plus H2S hydrogen sulfide give us manganese 2 plus sulfur. So, what is the oxidation number? We just calculated this one earlier on. Is plus 7. The first one we calculated is plus 7, so it's the same thing here. So we have oxidation number here plus 7. Here is, let's calculate this one. Hydrogen H2S is equals to 0. Hydrogen is 1 times 2 plus sulfur equals to 0. 2 plus sulfur is equals to 0. Sulfur is equals to minus 2. So here oxidation state is minus 2. Here is plus 2. The oxidation number of elements in their free state, in their neutral form, is equals to 0. So here sulfur is 0. I read that. I don't know, you don't have to go back to it. You have to listen or go check it out. So now this is what we have. We do our subtraction as usual. Manganese here, 2 minus 7 is 5. So I have manganese is 5. And let's call it sulfur. 0 minus this is still minus 2. So we ignore the sign, which is 2. So I cross multiply. Anywhere I see manganese, I put 2 before it. I see sulfur, I put 5 before it. So now, manganese here is 2 MnO4 minus plus 5 H2S equals to 2 Mn2 plus 5 sulfur. Okay, now let's see we balance for oxygen in the right side of the equation. We have 8 moles of oxygen here. So I have 2 MnO4 minus plus 5 H2S give us 2 Mn2 plus 5 sulfur plus 8. Alright, oxygen is what? 8 H2O. So now I have oxygen 8. But hydrogen now is 16. I have 2 MnO4 minus. Now, hydrogen is 16. I have to balance hydrogen this side. Plus, okay, now again. Since it's 16, and this side we have 10 hydrogen already. So I will bring in 6 hydrogen. Plus 5 H2S plus 6 hydrogen ion will give us 2 Mn2 plus 5 sulfur plus 8 H2O. Let's see, 2 times minus 1 is minus 2. Okay, this, there is no charge on it, so it's 0. This is plus 6. 6 times 1, we're balancing the charges. This times this is 4. 2 times 2 is 4, so plus 4. Now minus 2 plus 6 is plus 4. Plus 4. So we say our equation is balanced. As such, this becomes our official balanced equation, which we can use in redox or titration. So that's question number 2 in balancing of redox. Let's take more. Don't know the one that they likely bring. So let's take the third question here. We have MnO4 minus plus 5 ion 2 plus. Okay, give us Mn2 plus plus 5 iron 3 plus. Like we balance something like this. Now this equation here looks a little different. Be that they have they've gotten the dissolution number. Then the dissolution number, after the dissolution number, they've done the cross multiplication, so we just proceed, which is going to be faster for us. So now, having done that, the only thing left for us is to balance for oxygen and hydrogen. So oxygen here is 4, so I have my MnO4 minus plus 5, iron 2 plus give us Mn2 plus 2 plus 5 iron 3 plus we have 4 hydrogen, so 4 H2O. We have 4 oxygen, sorry, so we have oxygen here now 4. In the course of doing that, we have 8 hydrogen there, so put 8 this side. So I have my MnO4 minus plus 5 iron 2 plus 8 hydrogen plus give us manganese 2 plus 5 iron 3 plus 4 H2O. Let's check. 1 times minus is minus. 5 times 2 is 10. So we have minus 1 here plus 10 plus here is 8. Give us plus 2 plus 15. 10 plus 8, 18 minus 1, 17, and 17. Seems like they won't balance previously, but this one, they didn't start from the beginning. So let's take another question. I'll clean this one now. Yes. The third question will be the fourth. I think the fourth also. We have 2 MnO4 plus 5 C2O4 2 minus. This is a minus here, pardon me. Give us 2 Mn 2 plus 10 CO2. So here again they've done the needful. All we need to do is to balance oxygen and hydrogen. Now oxygen here we have 2 times 4 8. 5 times 4, 20. So 28 oxygen here. Oxygen, 28. Here, 10 times 2 for oxygen, 20. So we are going to balance for 8 moles of oxygen inside. So I come back. I have 2 MnO4 minus plus 5 C2O4 2 minus give us 2 Mn2 plus 10 CO2 plus 8 H2O. Now I have 8 oxygen now, so it's balanced. Now hydrogen this way, I have 16 hydrogen here, so I'll come back this way. I have 2 MnO4 minus plus 5 C2O4 2 minus plus 16 hydrogen plus will give us 2 Mn2 plus 10 CO2 plus 8 H2O. Okay, let's check if balancing of the charges. 2 times minus is minus 2. This is 5 times this is minus 10 plus 16. Give us 4. Is that all? Alright, let's see. Okay, good. Minus 2 minus 10 is minus 12 plus 16 is 4. And this is plus 4. So it's balanced. Let's move to another question, the fifth question, yeah? Okay, let's take this. 2 MnO4 minus plus 10 iodine minus give us 2 Mn 2 plus 5 iodine molecule. So they have calculated the dissolution state and they've done the cross multiplication. So let's balance for oxygen. Okay, oxygen and hydrogen. Oxygen here is 8. Yeah. This is 10 iodine. So I have 2 MnO4 minus plus 10 iodine negative give us 2 Mn2 plus 5 iodine plus 8. So I have
8 moles of water.
Okay, 8 moles of water. And now I have 16 hydrogen. To introduce this, I have 2 MnO4 minus plus 10 iodine negative plus 16 hydrogen plus will give us 2 Mn2 plus 5 iodine molecule plus 8 moles of water. Let's balance it. Minus 2 minus 10 plus 16 give us plus 4 only. 12 minus 12 plus 16 is plus 4. This is plus 4. So the equation is balanced. Yeah. So far, with our acute knowledge of oxidation state, oxidation numbers, we'll be able to balance all redox reactions whenever we come across them, most especially during titrations. So I will advise you to go through what we've done now religiously, patiently, and go through them one after the other, solve them again, balance them on your own, and see that you get them right. And when you do, you'll be proud you actually did. Thank you, and have a nice day.